haven't done the videos, I might not be well prepared, so I should be for these. Yeah, so very quickly, we did a big revision thing last time. But saw those mechanisms again. Yeah. So that's the old DHSS, yeah. And then we're saying, no, let's say that it's costly to get stuff out. So that's one change. Then we said, no, look, we can't just have Cobb Douglas here, we should have sort of something like this. And then we can start looking at directed technological change to save on the need for the resource, yeah. So that's one mechanism. Yeah, another one was multiple products, which each product have a different production function, and some of them need less, sort of intrinsically. For the same state of the economy, they need sort of less resources than others, like sort of teaching, or I can't remember what the example you had was now, but
I think
daycare,
it's daycare or something, yeah.
Compared to sort of international travel. So that was the other one, and the third one, which is what we're going to look at now, is this, yeah. So we have, and so Solo was talking about, well, if this is running out, we can switch to this. But what's actually more relevant, as it turns out, really since Solo wrote that in '73, it's become clearer and clearer that the vast majority of resources aren't running out anytime soon. The Earth's crust is a big place. But this kind of switching is still super relevant to sustainability. Why?
Because if you emit that much?
Because of pollution, yeah. So this is like coal or something. We want to get out of this to something else because this is so polluting. And so we're going to come explicitly on pollution in the next lecture, which is also part of today. Okay. So now I've got a bit of a dilemma because I haven't done a video. So let me just flick through this very quickly. Okay. So what have we got here? So, because typically in economics, it's like I was saying, all the models are massively simplified. So it's not like, okay, we know that ideally we would model the demand here in this kind of way, and we'd have maybe some directed technological change, and we'd have multiple goods and so on. But here we want to focus on this aspect. So we just collapse all that back to the Cobb Douglas. Okay, so that's this. Because we're not focusing on those aspects here. And then we need to bear in mind that we should have a think about, I really should try and find a better pen, because it's not going to, I'm afraid it's not going to show up on the video. Right, what was I saying? Yeah, we need to bear that in mind and think about, okay, is this going to be a big problem or not? Later on, kind of. But for now, we just go with this. Okay. And then we can look at the profit maximization problem for these guys, which is up there, yeah. And of course we get the fixed share of the resource R. Should all be happy with that by now, I hope. But then we're looking here, aren't we? And typically, often the best way to deal with this kind of thing is to sort of put a black box in between these sectors and this. So this could be, you could think of this as electricity generation, if you like. So this is like coal, this is gas, turn into electricity, and then these guys want the electricity, if you want to think of it in concrete terms. And then throughout this course we're assuming perfect markets, yeah, so it's going to be pretty straightforward. So then here we have R coming out and coming in, so I've called it XC and XD, yeah. Or I'll use little c's and d's, whatever.
Which are different resource formula.
Yeah, so this is the amount of coal, and this is, or that's, I guess C is clean, so this could be like wind, and this could be coal or something. Or gas, if you like, if you really want to think about tons of resources. And yeah, we dropped AR because it's just, if you're in Cordova, it's not really doing anything anyway. So then we've got this, which is what we're used to. And then we assume that productivities just grow in parallel. So we're not doing directed technological change here, we're just saying there's this overall productivity of all the inputs that goes up. Or in particular, the productivities of coal and gas or whatever it is just go up together. For now, yeah. So we're also sort of parking directed technological change for now and seeing what we can do in a simpler setup, how far that gets. So then we can take this A, we change those two to A, and then we can take them outside, can't we? Because we've got A to the epsilon to the 1 over epsilon once we've taken it out. So it's just like this. Okay, what's this C then? Yeah, because that's what's coming this way as opposed to... Oh, so in fact, we're not doing labour, are we? We've gone back to the other way. We've got a total production, Y, and some of it is going to consumption, and some of it is being used to extract the resources. So we've gone back to that way of doing it. Do you remember that discussion? Yeah, that is. You can do it either way, it's just the math is slightly different, but the results all come out the same. Okay. So, what's that top line there? Have a think about that. Check with your neighbours that you're all on message here.
Alright. I don't know how specific you're supposed to do it in the function for the first.
But which ones?
I would say it's like for electricity generating box thing.
Mm-hmm. Right.
These guys.
Okay.
What do you think? What do you think, Viola? So these guys, what's the revenue for these guys? Or the representative electricity producer, what's the representative electricity producer's revenue?
The sum of the other two revenues.
So that's its costs of buying these, right? But what's its revenue? So what's it selling? It's selling electricity, right? So its revenue is just WR, the price of electricity times the amount of electricity. And then its costs are like, I'm not sure what notation I've used, but it should be WCXC and WDXD, I guess. Okay, so is this WRR? It is, isn't it? That was the expression we had for R from the previous slide. So sort of CES function of the two inputs. So if you think of electricity, you might say, look, can't we just add them together? Wouldn't they be perfect substitutes? Typically, actually not. If it was coal and gas, they might be. If it's like wind and coal, they're not, because the wind is quite tricky. But if you think of this as like tons of iron and this as tons of aluminium, then clearly not perfect substitutes, are they? Because there's some applications like we'd really, really rather have iron here, and there's other where it's like, oh, aluminium, brilliant, and there's others where it's like a toss-up. Which means that the sort of ideal is to have a bit of both kind of thing. And then if you have loads of one and less of the other, then the price of the one that you have less of is going to go up relative to the price of the one you have loads of. Remember the coins? Janina's coins, yeah. That means they're not perfect substitutes. And it's the same with, say, wind power and coal power. If you have loads of wind power, like what do the wind producers in Germany when the wind gets up? What happens to the price of the electricity the wind generators produce? Anyone know? I sort of singled you out because of the sort of German story, because you have a lot of wind power in Germany, right? Does anyone know? Well, can you have a guess? Like, imagine it's really windy.
It's the price from the generation of
Yeah, the price. If this is the wind, if you've got a windmill here in this box, and it's suddenly really windy, what is WC what's going to happen to WC? These prices are set by the minute, yeah. So it's not like there's some annual agreement. There's a market that is. It's like a share market or something. The price is changing the whole time.
Should it go down?
Right. Any thoughts about how much? Basically, it goes through the floor, right? Because basically, the coal stations and things, you can't turn them off. Because the concrete will crack and stuff, you know. You can't let them go cold. So you've got this electricity coming in from the coal, and then you're topping it up with the wind. Then suddenly, instead of like 10 gigawatts of wind, you've got 100. And it's like, well, who's going to use all this stuff? You can't sell it. It's like having a mountain of left shoes. So they're not perfect substitutes. When you have a lot of one, its price goes down. Okay, anyway, yeah, just a quick justification for why we're not going with perfect substitution anymore. Okay, so then, having got that profit function, we can do first order conditions, can't we? And I guess that's what I've done here. It is, yeah. I've done first order conditions. We'll do that. I'll do that in the video. But we end up So what's this saying? It's saying that the guy in the black box here, how much is she spending on, yeah, we'll make her a she. How much is she spending on buying wind power compared to what she's spending on coal or whatever? And it's this. We can also express this in terms of quantities. I don't even remember, there was that slightly tricky business. I think I just did that in a video of switching from the having quantities on this side to having prices on this side. It's kind of tricky. So I guess this way of expressing it makes sense if you're looking at like iron and aluminium, because you sort of got these extraction costs for the iron, you've got the extraction costs for the aluminium, that's going to be the prices. And then it's like, okay, how much? So they're kind of, you could think of those as sort of exogenous, and then this is the shares. And we're thinking, yeah, so what's epsilon for these resources? This is super important.
Did we say there were 4 substitutes, right? Or did we say there were?
We've said that they are things like coal,
Not
gas,
four.
coal, wind, iron, aluminium.
Okay.
And we've said they're not perfect
Okay, so
substitutes.
they're substitutes, but not so it's positive. Epsilon
Right.
is positive.
Yeah? It should be bigger than 0, typically, if they're like good substitutes, rather than poor substitutes. I find there's some people say, oh, they're substitutes if it's bigger than 0, and complements if they're less than 0. I really hate that terminology. It doesn't make sense. Like, there's always a degree of substitutability between inputs, unless you've got Leontief. It's just they're not very substitutable, or more substitutable. There's also always a degree of complementarity between inputs, unless you have perfect substitutability. But they should be relatively highly substitutable, or epsilon greater than 0, which means that if a resource gets cheap, one of them gets cheaper, how much do you spend buying it? Have a think about it. More or less.
So they are substitutable, and if the price gets cheaper or less, then you would spend more on it.
Right. So if you just do the math, if WC goes down, this goes up, doesn't it? And this is positive. So this goes up. So you're spending more on the stuff that got cheaper. Does that make sense? So imagine you're using iron and aluminium to make stuff, and they're super substitutable. You don't really care which you use. And then the aluminium gets cheaper. We'll have not just sort of more aluminium, but like loads more. Yeah.
Whereas,
If we think of labour and the resource, we tend to think not very substitutable. And if one of them gets cheaper, we still buy about the similar quantities as before, and its share goes down when epsilon is negative. And that's the same expression, yeah. But epsilon negative, then when this gets smaller, if this gets bigger, this gets smaller, yeah. When that's negative. Okay. So, cheaper input takes the bigger share, price goes down, the share goes up even more. And we can do some more math and actually work out the price of electricity, which is, you can do sort of first order conditions, or you can just say, look, we've got perfect market prices, unit cost. Again, I'm not going to go through it because I'll do it on the video. So, yeah, let's just skip the math because I'm going to do that on the video. And what we find is that from this math is that if prices are constant, so if we've got like iron available at some price, aluminium available at some price, and we've got some underlying technological progress, and I've even thrown in some late growth in population here, I don't know why, I generally try to keep that out of it, then the total quantity of the resource will get increased at the same rate. Yeah, more resources will get sucked in as the economy grows. And if these are staying the same, actually the quantities of XC and XD will also grow in parallel. But if WC and WD are not constant, then things are going to change, aren't they? And especially if WC over WD goes down, this is just revising what we just talked about 1 minute ago. What's going to happen to XC over XD?
It'll go up.
Right. And how much?
A lot.
Yeah. More, kind of in percentage terms, more. So, implying then that WCXC over WDXD will go up. Yeah. The share of the one that got cheaper goes up. Okay. And then, basically what I then do with this is just see if this really simple model, take it to the data and see how well we can match some data with it. And as we just talked about, this is not then saying, okay, if we match the data, it's not, okay, job done, but it's still kind of interesting. So what have we got here? This is global product, so it's like GDP globally. This dotted line is expenditure on coal. This is expenditure on oil. And this is the coal price, and this is the oil price. Okay. So this is just data. No model yet. Then what have we got? So we've changed the scale here, but if you look here, -4 to 0, so it's the same data. Global product. This is coal plus oil expenditure observations, this line. And the dashed line is from the model. So we stuck the prices into the model and found and chosen a value of epsilon, basically, and the gammas, I guess, to try and get a fit. So what this is basically saying is, it's saying something about the factor share of coal and oil together, isn't it? What's it saying about the factor share of coal and oil together? According to the model, it should be perfectly constant, right? And this is the data. We know that there's going to be fluctuations in the short run because we're not capturing short run stuff, you know. By choosing Cobb-Douglas here, we're saying, okay, this is long run, yeah, we're automatically saying we can't say anything about short run fluctuations here. But this constant share assumption, it's not perfect, but it's like, we're not far off. Yeah. this one, can you see the dotted lines here? The dotted line.
No.
Sorry, is it going
Oh
up
yeah,
and down a
oh
lot?
right, I see, it's really unstable.
Yeah, okay.
Yeah, there's a lot of fluctuation. But if you try to focus on the trend. So what do you think this is? If you look at the legend at the top, what are those two curves? What do you think? So what's obs and mod? So it's the same as this one.
Mm. So, observe.
Right.
Model.
Yeah. And then shares. So if you look here, where mathematically, what would that be? It's here somewhere. So this is the shares, isn't it? The shares relative to each other. So for the continuous line, we've just taken the data for the prices and the data for the quantities and calculated this and plotted it. And what have I done for the dotted line? Somehow I've used a combination of data and model here. So the question is, which part comes from the data and which part comes from the model? Did you have it? So remember, I'm sort of assuming that there's these exogenous prices coming from the mines, so to speak. And then I'm looking at I'm using the model to get the quantity. So in the continuous line, I've just taken the model, the data for prices and quantities. In the dotted line, I've taken the data for the prices, and then I've calculated, given those prices, I've calculated what quantities the model predicts. Okay. So what we can see is the model is doing, I would say, a very good job of predicting how the relative quantities react to changes in the relative prices. So these fluctuations, this is no problem because we've already said that we can't deal with the fluctuations, we're only looking at the trend. Okay. So up until the point when the oil price started fluctuating massively, they're tracking each other really, really nicely, and then it gets a lot trickier. Because we know that when they're in the short run, these price fluctuations, which were very large in the 70s, yeah, cause all sorts of stuff, but it's not captured in the way it's set up. Okay. So what is this really about? It's about here's the coal price, yeah, trend. Pretty flat, but very slightly up, yeah. Here's the oil price, pretty flat, but significantly down, at least if we start way back. So what do we expect to see with the shares? We expect to see the coal share declining as the oil price goes down compared to coal. And that's what this is, I suppose. It's not clear that this must be, is this oil over coal or coal over oil? I can't even get my head around it. It must be oil over coal, mustn't it? Because it's going up here. The coal share is declining, the oil share is going up. So what we're seeing is the oil share goes up as the oil price declines. Okay. And the parameter's kind of interesting here, 0.76. So what's that saying about the degree of substitutability? It's like super high, right? In the long run. In the short run, no. In the short run, the oil price goes up. You don't say, oh, we'll stick coal in our cars or whatever, or we'll stick coal in our sort of oil-fired, or, yeah, if you go back here, oil price goes down. In the short run, it's not, oh, we'll pour oil into our coal-fired power station. It's not going to work. But on a sort of 50-year time scale, because there's a lot of heavy capital goods in these sectors, but on a 20, 30, 40, 50-year time scale, it's like you change the way you're doing things to use the input that got cheaper. This is the same thing for iron and aluminium. And again here we see the iron price is flat, the aluminium price is going down. The share of iron and aluminium together is very closely tracking GDP. So this sort of long-run idea that there's for whatever reason, there's some kind of conductors. When we just take a bird's eye view and look at the long run, it's as if there's a conductor. It seems to fit very well. And the shares react exactly as we'd expect. Slightly lower degree of substitutability. Does that make sense with a slightly lower degree of substitutability? I mean, I don't know, you'd need to talk to an engineer. But to me it makes sense, I don't know. Like, energy, some energy, that's the Swedish thing. What would you say? I don't know. But it's like you don't want to make aeroplanes out of iron, you want to make them out of aluminium, right? Because you want the lighter stuff for that. Whereas other things, it's like, no, let's use steel kind of, because for other reasons. But there still is plenty of substitutability there. You know, it's not impossible. So yeah, to me, it's not surprising that these numbers make a lot of sense to me. Like a very high degree of substitutability for coal and oil, and somewhat lower for iron and aluminium. So this is kind of cool. To me, it's sort of showing just how far you can get with this incredibly simple model without any directed technological change. It's just this sort of, the underlying technologies are there, but it takes time to adapt. It's more about actually shifting your capital. So we've got this coal-fired power station. We know how to make electricity out of oil, say, but at the moment all our power stations can only run on coal. So that's why you get the change over time. In the short run, the very low elasticity. In the long run, much higher. Elasticity is substitution, according to this way of thinking. You don't actually need to invest in new technology. You know how to do it, it's just you don't have the capital. Okay. So that's the point so far. Then, if we want to, let me just see how much we've got here. If we want to, we can throw in technological change. What's going to happen Let's just do some intuition on that and then take a break. Okay. So, if we throw in technological change, yeah, have a think about that. Okay, have a think about it. We're going to stick with the same production functions. So let me put this down. So what do we have? We had R is A gamma C xc plus gamma D xd. And then we have these. Yeah. Okay? Something like that, wasn't it? And then we're going to throw in directed technological change. So just have a think about what are we going to need to do with this, and what kind of results should we expect? Okay. Think about that for 3 or 4 minutes. Have a chat. I'm going to go and get a cup of tea. Then we'll talk about that for 2 or 3 minutes. Then we'll take a break. Then we'll actually sort of do it briefly. The main thing I want you to get out of this is actually just getting a grip on the intuition, and then I'll put the video up. So just think about that for 2 or 3 minutes, okay?
Like AC and AD in the equation.
Yeah, great. So it's quiet because you've finished minutes ago. So where should I put the AC and the AD? Inside these brackets or outside?
Outside, maybe.
Maybe. No, they always need to be inside, yeah, because they need to get the units, yeah. Because remember, this is, if you think this is like, think of them as productivities, and this is like tons of coal per year, or some, whatever they are. And then we need like widgets per ton times tons per year. So it has to be inside. We can't have this epsilon, one raised to the epsilon and the other not. So we need to go back to this which we actually had at the start, yeah. I don't know if you remember I put this up before. Okay. And if we stick with the same epsilon as we had in the simulations before, but then we say, look, these vary depending on how firms invest. So that was the next question. What's going to happen to the simulation results? What's the model going to predict compared to what it predicted before? So, if you think of, or do you have an answer to that? No. So think of the iron aluminium case. Okay, let's choose iron aluminium. What happened to the relative prices? One of them got cheaper, which? Okay, you don't remember, it doesn't matter. It was aluminium. Why would aluminium get cheaper? I guess it really depends. No engineers here, right? We've been there before.
But it's easier to extract. So it doesn't, like when productivity grows in the sector, it doesn't affect cost as much. Well, iron is quite expensive to extract because they have to like move clear and stuff.
Yeah, you're in the right ballpark in terms of thinking about things. But you haven't got there. So, like, was there an aluminium age? There you have Stone Age and Iron Age and stuff. Which do you think is easier to extract? When did we start using aluminium? Any guesses? Basically, we only really discovered aluminium about here. Okay, and it's much harder to extract, technically. Okay. The aluminium oxide, it's super hard to turn aluminium oxide into aluminium. So, and until you could do that, nobody really knew there was this stuff called aluminium. You just had this rock called bauxite. Or bauxite? Yeah, yeah. So then, why would we expect the aluminium price to go down? We discovered aluminium about here, sort of 1870 or something. So the price, this is a kind of directed technological change story, I would say. That, when we discovered it, we still don't really have a clue how to extract it, or it's super expensive and so on. But then we start getting the hang of it more and more. Whereas iron is super straightforward, basically. You just stick it over some coal, hot coal, and you turn iron ore into iron. Super straightforward. So that sort of bundles along and costs about the same over time. But because this is so tricky, as we get better at high-tech stuff, the cost goes down. Okay. And then according to this model, just driven by this, we start using aluminium in more and more applications. Yeah. But what if we threw in directed technological change as well? What?
Wouldn't it only boost the state? We would invest more in the technological change.
Exactly. You got it. Because remember, when it was labor and the resource, it sort of buffered the effect, it sort of dampened the effect, didn't it? Because when something got cheaper, its share went down, and then we didn't bother investing in it anymore. But here it's the opposite, isn't it? The aluminium got cheaper, its share compared to iron goes up. We put more effort into learning how to use aluminium instead of iron, and that will boost the share even more. Okay. And actually, when you do the math, if you assume what is often assumed in the literature, which is, so what is often assumed in the literature about AC and AD and how they grow, which I was complaining about before.
That they don't affect each other.
Right, that they are in this stuprör separate, and there's no lab equipment that is used in both. They're totally separate. If you assume that, then you basically get this. That if one of these has a bigger share than the other, then you'll invest more in that one. It'll get cheaper. The share will go up, you'll invest even more, it gets even cheaper, the share goes up even more, and there's nothing breaking that process, as these are totally independent of each other. So you end up in a corner using only one and not the other at all. Okay, so that is the sort of turbocharged process. That's the sort of extreme case, if these are just totally independent of each other. But if they're like strongly linked, then you could still get results which look more or less like we actually get. But then you'd say that the reason this sort of short run elasticity is low, but the long run is higher, I sort of said it's because we have the knowledge that you switch to capital. But you could also tell a story that actually it's not just about switching capital, it's also about investing in knowledge. But the returns to that investment are highly limited because these are kind of locked together. Not rigidly, but one can't just grow massively compared to the other because they're building on the same knowledge. The shoulders are standing on shoulders across the sectors. Okay. So there's sort of been big claims made for the power of the DTC mechanism to drive shifts from using one input to using another. But they don't stand up when you look at the data. Okay. Because if the DTC mechanism had this amazing power, because these grew independently, then we wouldn't be seeing this. We'd be seeing that basically, typically, you would be locked. If we think of this, typically, if this is like iron and aluminium, when we discover aluminium, you're already down here, and aluminium doesn't have a chance. It'll never get anywhere. If it somehow did get somewhere, then it would just take over, and iron would disappear. But it's just not what we see in the data, right? And this is super relevant to climate change and pollution, right? Because if you believe in this story, then it's just like we just need to get renewable technologies up to the top of the hill, and then we're sorted. They'll just take over. We don't even need a carbon tax. Okay. And there's a paper in the American Economic Review, which is the most prestigious of all the economics journals, which is making that claim. From 2012. It's on the reading list. But it's nonsense. Yeah. Okay, so that's what we'll talk about after the break. So actually, we've done more than what I said we did. I've basically taken you right to the end of this now. We're not going to go through this now. We'll do that in the video. It's basically the same math as we already did for this case. Labour and the resource. But now because epsilon changes sign, the math is the same, but the interpretation and the results are flipped. Okay. Time for a break. How